Welcome. Today we will be taking a look at the notes worksheet entitled Applications with Equations Day 2. This represents a continuation of the previous day's lesson and gives us an opportunity to do just some more examples together. So let's go ahead and do some more uniform motion problems, as it said, the type 3, I guess, that from what we talked about. And we'll go ahead and do 2 examples of that, and then we'll do 1 more job sharing. So example 1. 2 children, 224 meters apart, start walking toward each other at the same instant at rates of 1.5 meters per second and 2 meters per second, respectively. All right, very nice. When will they meet, and how far will each child have walked? All right, so let's see what's going on here. Maybe try to be visual with this. You know, I've got 224 meters in between the 2, something like this. Here's little Timmy right here, starting to go this way. Here's little Tommy right here, going to start to go this way. One is obviously going faster than the other, and so as a result, they're not going to meet halfway, just after how many seconds, and how far will each child have walked. All right, fair enough. I think we kind of know the drill here. So this, with these uniform motions, obviously we're talking about a distance traveled at a constant rate and taking time. So distance, rate, and time, pretty easy. And let's go with the 2 children. What did I say, Timmy and Tommy? All right, let's stick with it. Here's little Timmy. Here's little Tommy. Let's get them walking towards each other, and we'll go for it. Now, I'm going to fill in my table a particular way. It just so happens there are probably 2 ways to fill out the table, 2 different equations to create, but getting the same results. So we'd love for you to take a moment and pause the video and see what you come up with in terms of your distance, rate, and time. See if you come up with an equation. I'm going to give you my scenario in just a second here, and then I'm going to do it just a secondary way. I'll do that faster, but just showing you that there's an alternative. All right, well, maybe you did it, maybe not, but regardless, let's fill in what we know. Without question, it seems like the 2 rates are given. We have to put those in. Those are going to be constants, and put them in your table. Doesn't change. All right, now we have to kind of think about what we want to do here in terms of the variable. I personally like putting the variable under the time. You know, it does ask when they will meet, and so as a result, I would call that x right there. So Timmy is going to walk for a certain number of seconds. I have no idea how long. But because they start at the same instant and they're going to meet, however long little Timmy walks, little Tommy walks the same amount of seconds. So if this is x right here, again, same time, so same variable. And that's kind of nice putting it together like that because, again, once we have a numerical value in one category, a variable in the other category, we use those to get the third category. And so, guys, rate times time. So the distance is going to be 1.5x for Timmy, 1.5 meters per second for a certain number of seconds. And little Tommy, 2 meters per second for a certain number of seconds, so his distance traveled is 2x, excuse me. And as a result, everyone, it looks like there's an equation to be had here. Look at the information in the problem. Look at what we haven't quite accounted for just yet, and let's see if we can apply it to this particular column right here. Timmy is going to walk 1.5x meters. Tommy's going to walk 2x meters. In total, they're going to walk 224 meters. So again, just certainly one way to pull this off here. Kind of allows us to create a nice simplistic equation. Going to combine these together. And of course, I do get 3.5x equals 224. And I'm going to, I can fit it in down here. And it looks like when I solve that, so let's see if I can do this numerically quickly in my head. Oh boy. I'm getting about 64. I should probably check that. So I'm getting 64 seconds. Let's verify before I go further. So bring up my calculator there, 224. That's the distance between them. And divide by 3.5. Whew, okay, I was right. Good, so in this case, 64 seconds would do. All right, so let's see, 64 seconds was the answer right up here. That's looking really nice. And then it does say how far will each child have walked. And so if this is 64, again, just kind of throwing things into the table here. You can do this or not do this. It's your call. Could I probably find the distance for Timmy and the distance for Tommy here? Yeah, probably. Let's see, 1.5 times 64 here. I'm getting 96 on that. So 96 meters for little Timmy. And then this one's a little easier for me. 2 times 64, how about a $1.28? And so 128 meters. All right, that looks great. Okay, distance, rate, and time. Now, if you like kind of this setup right here in the table, like the equation produced, beautiful. Works nicely. Again, I just want to quickly show you a secondary way, and you can fast forward if you're satisfied. But I am just curious if maybe you thought of a different way. Same deal, again, distance, rate, and time. We said this is going to be written in stone right here. That has to be the 1.5 and the 2. But basically, I've seen students in the past, they'll put the variable under the distance because it does ask how far will each child have walked. And so what you can do is say, all right, well, Timmy's going to walk X number of meters. And here would be my question to you. If Timmy walks X meters, what does Tommy walk? And in this case, I hope you would say it's 224 minus X. And so now, guys, your variable happens to be under the distance. Could we still potentially use distance and rate to come up with the third column right here? Yeah. Distance divided by rate. So the time it takes Timmy to walk is X over 1.5. The time it takes Tommy to walk is 224 minus X over 2. And this is what I like about it. Not only can you fill the table in, but can you come up with the equation? That's the key. And in this case, what do we know about the times that they walk? They're the same. And so your equation would be this. Again, just two different looks at it. You get the same, so I'm not going to go ahead and solve. But if you solve there, I have a feeling you'd pull off a 96 right here, and then obviously this would be 128. And then go ahead and solve for the time, and we'd get 64 seconds. So just two different ways. You know, pick your poison, basically. Great. Let's go to the next. Example 2. So a tugboat can travel up the Mississippi River 66 miles per hour in the same time it can travel 90 miles downstream. Okay? If the current is 4 miles per hour, find the boat's speed. All right, very nice. I would probably have to tell you off the bat here that this is an extremely oversimplified version of the reality here, but I don't think this is exactly how wave mechanics works, but this is typically how these problems are solved, so I'll go ahead and show it to you regardless. So even though it is probably a drastic oversimplification, we'll still go with it. So guys, distance, rate, and time. Talking about the distance up and down, particular rates. In fact, that's what we're trying to find here, the boat's speed. And the time in there as well is sort of given. So it looks like we're going up and we're going down. Let's get that going. Let's go with the constant first. That's the easiest one. So a tugboat can travel up the Mississippi River 66 miles, up 66, down 90. All right, so now here's where the wave mechanics come in. Oh boy. So if the current is 4 miles per hour, find the boat's what we would call still water speed. So again, just the short version of the story would be here. As the current is going down and the boat is traveling downstream, the current is helping the boat's speed, aiding the boat's speed, where if the boat is traveling up, the current is a deterrent to the speed. It is a hindrance. And so typically what we have is the still water speed of the boat. That would be the speed of the boat without a current. And what we would do very simply is add or subtract the speed of the current in order to get the overall boat speed. So long story short here, if we're going upstream, we have the boat's still water speed, and we would subtract the current speed. And if we're going downstream, very simply we would have the still water speed, and we would add the current's speed on top of it to make it go faster. Obviously, this one slows it down, this one speeds it up. There is your, and what was the phrase I used? Dramatic oversimplification, but it is what it is. Okay, so let's give it a try. We've got our distance and rate. Let's use that to create the time. So this is going to be 66 over x minus 4. This one, of course, is going to be 90 over x plus 4. That sounds good. And the question will be, what equation can we create here? And I think you would see that the times are the same. I think it says it specifically in the problem. So the time upstream is the same as time downstream now. There we go. So a little cross multiplication here. We'd love for you to kind of pull this off. Just go ahead and cross multiply. This is equal to that. And so I get, when all is said and done, and you could pause the video for a moment if you'd like before getting an answer here, but again, just cross multiply that. I'm pretty confident, that you can pull that off, and you get x equals 26. So that would be the still water speed. So it just kind of talked about the speed potentially going up and down. And so you can see going up, it would be 22. And I believe we're in miles per hour here. Those were my units. And then down, I think, would be the 30. And there you have it. Nicely done. So again, just working with the current, what we would call the still water speed, either adding or subtracting the current of the river to aid or deter the true speed. All right, let's move on. So the last one here, we've gotten a little look at this, job sharing. So this one is quite a bit harder. So we're going to be a little careful on this, try to walk through. And I would say after we do this problem, spend about 3 or 4 minutes just reflecting on it and kind of look at the breakdown. Obviously, when I do these problems for you, I try to give you some questions that lead us into the equation. But it would be good to reflect on that a little bit before just letting it go. So here we go. Let's give it a try. Example 3. Bruce works for 15 minutes fixing his hot tub. Then Angela helps him, and together they finish in 20 minutes more. If Bruce could have done the job alone in an hour, we'll go 60 minutes on that, by the way, so let's get everything in the uniform time. So in 60 minutes, how long would Angela take alone? All right, very cool. So one thing we have to be concerned about here is that part of the job is done independently before they start working together. So let's go to letter A, and I think this is a good preliminary question here. So take a look at this piece. So Bruce has already done part of the job by himself. Then Angela helps. And I guess letter A asks, how much of the job is left when Angela begins helping? All right, so take a look at the information in the problem. Bruce is going to work for 15 minutes starting it out. And he can do the job in an hour. That's the key. So it's all about Bruce, at least initially. So how much of the job is left when Angela gives him a hand? And I hope you would say that 3/4 of the job is left. Everyone okay with that? So when Angela starts helping, 3/4 of the job is left. All right, that is good. Now let's start developing our variables and our ideas. Remember, we talked about this as we want to think of it as in terms of how much can be done in a single unit of time. Okay, so let's go to letter B. How much of the entire job can Bruce complete in a single minute? So you start the stopwatch on Bruce. 1 minute later, you stop the stopwatch. How much of the job can Bruce complete? He can do a 60th of the job. Takes him 60 minutes, and we talked about this. This is basically a rate, so to speak. And so he can do a 60th of the job in a minute. Okay, good. Letter C, guys, on to the next piece. How much of the entire job can Angela complete in 1 minute? All right, well, if you kind of look at the problem, by the way, isn't that exactly what we're asking? How long would Angela take alone? So in this case, this is going to be our T, right? how long would she take to do the job alone? So it's going to take her t minutes to do the job. So how much of the entire job can Angela do in a single minute? So we start the stopwatch on Angela. We stop it a minute later. How much of the job can she do in that single minute? It takes her t minutes, so she can do 1 over t of the job in a minute. So let me just go ahead and been kind of doing this on the last time we saw it. So 1 over t there. So at this stage, we have how much of the job Bruce can do in a minute and the amount of the job that Angela can do in a minute. Obviously, guys, we're going to add those together, and that would be equivalent to how much they can do together in a single minute. But the problem is we need to kind of investigate that piece a little further. That is going to be, just FYI, that's going to be this letter F right here. But before we can do that, I think there are a couple preliminary questions to answer. So let's do letter D. It says, how long does it take them to do 3/4 of the job? All right, so remember what we said. They still have 3/4 of the job to go, and it does take them 20 minutes more to pull that off. So make sure you have that piece. It takes 20 minutes to do 3/4 of the job. All right, now here's actually a little preliminary equation that's coming our way, guys. If we're going to figure out how much they can do in a minute together, we should probably figure out letter E. How long would it take them to do the entire job together? All right, so let's use letter D to come up with letter E. So 20 minutes was 3/4 of the time that it takes for them to do the entire job. Everyone okay with the way I said that? So this 20 minutes right here is equivalent to 3/4 of the time for the entire job. So I'm going to do it just like that. Interesting. And so if I go ahead and divide by 3/4 or multiply by 4/3, I'm getting this, just again, very quick one here. Now, not the ideal number, but this is how long it would take them to do the job together. All right, so this would be 80/3 minutes. Okay, make sure we have that piece in place. So that's how long it takes them to do the entire job together. And then, now we can do that letter F. That was missing. So remember the idea here, of course. Basically, the amount of the job that they can do in a single minute is the reciprocal of the time that it takes to do the entire job. Remember that piece, of course? It took Bruce 60 minutes, so he can do a 60th of the job in a minute. Angela, it takes t minutes, so it's 1 over t of the job in a single minute. And so what we have here, if it takes 80/3 minutes for them to do the entire job together, then it's going to take 1 over 80/3 in order to do it in a single minute. All right, which happens to be, again, it's just the reciprocal, so if this freaks you out, please, ask about it. But I would argue that they can do 3/80ths of the job in a single minute. Interesting. Okay, because we had to work on that piece. We didn't know how much they could, or how long it would take them to do the job together. And now we can apply it as a rate. How much can they do in a single minute of time? And they can do 3/80ths of the job in a single minute. All right, guys, our equation's ready. So it says, write an equation and determine how long it would take Angela if she worked alone. Let's get our t. And so here's the idea. We start our stopwatch, and a minute later we stop it. Bruce can do a 60th of the job in that minute. Angela can do 1 over t of the job in that minute. We add their individual contributions, and that's how much they can do together in a single minute. And there's your equation. Wow, really nice. And you can see it's just a good rational equation here. Probably want to do a little LCD on this. I'm going to go ahead and do that, just a good little review from a few lessons ago. And I'm seeing an LCD of 240t. So see if that works for you, 240t on that. And so 240t, well, 240 over 60 is going to be 4. So how about a 4t right here? Distribute this into this one, guys. What happens to those t's? They're gone. So 240 times 1. Looks good. And then over here, let's see what we have going. I have 240. I can divide that by 80. That's not too bad. So 240 divided by 80 will give me 3. So this is 3 times this 3 is 9. And then times t, I'm getting a 9t on that. And again, if you want to grab the calculator, you're more than welcome to. Just do 3/80 times 240. Should give you 9. And then obviously with the t. Bring over the 4t here, and I'm sorry, I'm going to have to bring this on up. But I'm getting that 240 is equal to 5t. And let's go ahead and divide that over. I think I've got this one. Looks like 4 and 8. I'm getting 48 minutes. And you can see quite an interesting and more difficult variation of job sharing when we did this piece. Bruce works alone for 15 minutes, then Angela helps. And so working on that piece, we had to kind of really do some good math, a lot of preliminary work before setting up this equation down here. All right, great. Again, this is not a problem that I would say you can just look at and one time through and be like, oh, this works perfectly. I would take a little time. I would, after you shut the video off, I would just look over one more time and just really kind of see this equation in action. How we got this, pretty straightforward. How we got this, pretty straightforward. But really, it's this piece. How did we get it? Why did we need it? And then obviously, it sinks in beautifully to this equation. All right, so again, just some more practice with these applications. They can be difficult. The setting up these equations, it's 90% of the battle for sure. So please check in with me, help each other out on these. Sometimes talking things through really helps the understanding piece and the learning piece. Great, well, thanks so much for listening.